Hello everybody, my name is Teodora, and in this presentation I will talk about our work on definition and density-based estimation of calibration in object detection. This is a joint work with Aleksei Tiulpin and Blaschko. The overview of the presentation is as follows. I will first give a brief introduction and motivation for investigating this problem. Then I will present our definition of calibration as well as our estimator of calibration error. Next, I will present some of our empirical results and I will wrap up with some conclusions. We are witnessing an impressive predictive performance of deep neural networks in various computer vision tasks. However, they tend to make overly confident predictions, and this prevents their widespread use in safety-critical applications. In these settings, it is especially important that the models are well calibrated, which means that their confidence scores should accurately reflect the uncertainty associated with their predictions. Calibration errors have been proposed in the literature to assess the quality of uncertainty estimates of a given classifier. In recent years, there have been multiple advances in the field of calibration of neural networks, but most of these efforts are primarily focused on classification tasks. In this paper, we argued that the field of object detection lacks a general definition of calibration and estimation of calibration errors. Defining calibration for object detection is a challenging problem due to the variability of detectors. In particular, there are ambiguities related to how many bounding boxes are returned, how to select a detection confidence threshold, what is the intersection over union threshold for considering a correct detection, and so forth. There have been a few recent attempts to define calibration by either replacing accuracy with precision in the standard classification definition, or by requiring that both classification and localization performances jointly match the confidence score. In our work, we propose a general framework that unifies these existing definitions and is flexible to parameterize the notion of a correct detection. We also derive an estimator of calibration error relying on kernel density estimation. So let's look at this definition. Intuitively, calibration requires that the confidence score of a prediction should be aligned with some notion of correctness. In object detection, assessing correctness is more nuanced than in classification because it involves evaluating the degree of overlap between two sets of pixels. In order to define a family of calibration errors that considers this degree of correctness of a given prediction, we introduce a similarity measure L, for example IOU, and a so-called link function, which can be, for example, a threshold or an identity function. We denote the correctness of a detection with Z, which can be a discrete random variable in case the link psi is a threshold function, or a continuous random variable when psi is a continuous function, such as identity. Then the calibration for object detection is defined as shown on the slide. From this general formulation, we can also recover the two definitions used in prior work. If psi is a threshold function, we obtain the standard classification definition, where z equals to 1 denotes an accurate detection in the sense that the IOU between predicted and ground truth bounding box is above some threshold. If psi is an identity function, we require that the confidence score matches the degree of correctness, for example, computed via IOU. Now that we have the definition of calibration, we wish to find an estimator for calibration error, which measures the degree to which a notion of calibration is violated. For this, we rely on kernel density-based estimators due to their preferable properties over binning-based estimators. The derived estimator shown on the slide is consistent, asymptotically unbiased, and differentiable almost everywhere. As part of our experiments, we investigate the performance of the proposed estimator, both as a metric to evaluate calibration error and as an auxiliary loss function used for train time calibration. We use three popular object detectors with different architectures. As baselines, we compare against temperature scaling as the most popular post-hoc calibration method, and with TCD, which is another auxiliary laws designed for calibrating object detectors. We measure calibration with our estimator, as well as 2 other binning-based estimators for comparison. We start by comparing our KDE-based estimator with a binning-based estimator called detection ECE on synthetic dataset where the ground truth calibration error is known. From the shown figure, we observe that DECE and our estimator have similar performance and both yield good estimates with a few thousand points. Next, we analyze the calibration performance of 3 popular object detectors on COCO, Cityscapes, and Pascal VOC. We estimate calibration error across different sizes of objects and for different thresholds for the IOU overlap. From the shown table, we can first notice that modern object detectors are intrinsically miscalibrated. We also observe that RetinaNet and FCOS have lower calibration error than faster RCNN, which may be attributed to the use of focal loss for the classification branch of RetinaNet and FCOS, which has been empirically shown to improve calibration. We can also notice that different metrics can reveal more nuanced insights about the calibration of the detector. For instance, both RetinaNet and FCOS demonstrate similar calibration errors when detecting small objects across datasets. However, FCOS has superior calibration scores for medium-sized objects on Cityscapes and Pascal VOC. In the final set of experiments, we investigate the performance of our estimator when included as an auxiliary loss to the task-specific loss of each object detector. On the left, we show that our estimator effectively decreases calibration error while maintaining similar detection performance. On the right, we show that the calibration error can be decreased also by fine-tuning pre-trained models even for a few epochs with our loss. To conclude, our study puts forward a novel and principled view on calibration in object detection. Specifically, calibration in this setting is a quantity that depends on the choice of a measure of correctness of a prediction. We also proposed an estimator of calibration error and showed that it performs equally well as existing binning-based versions, while offering superior statistical properties. In addition, due to its differentiability, the estimator can be directly included as part of both post-hoc and train-time calibration setups, leading to substantial reduction in calibration error while maintaining similar levels of AP. Thanks a lot for listening.